Hello there, and welcome to Sleepy Science. Somewhere in the universe, there are regions where space does not behave like space, where direction collapses into a single outcome, where time stops being a shared experience. These regions are not theoretical. They exist right now. One of them is shaping our galaxy in silence. A black hole is not an object waiting to pull things in. It is a place where the rules that normally protect reality no longer apply. And every strange fact you're about to hear comes from that failure. Most people imagine a black hole being born in a huge blast, with light, fire, and shockwaves racing through space. That does happen sometimes, but not always. Some black holes form in a way that is almost completely silent. No bright explosion, no clear signal, just a star that suddenly stops holding itself together. A large star stays alive by balancing two forces. Gravity pulls everything inward. At the same time, energy from nuclear reactions pushes outward. For millions of years, these two forces stay in balance. The star looks stable from the outside, but that balance depends on fuel. When the fuel runs low, the outward push weakens. Gravity does not weaken. It waits. In some stars, when the fuel is gone, the core collapses so fast and so cleanly that the outer layers do not explode outward. Instead of a supernova, the star falls inward on itself. This is called direct collapse. From far away, almost nothing changes. There is no bright flash to mark the moment. The star simply disappears from view. What remains is a black hole that formed quietly. Astronomers sometimes call these failed supernovae. The star does not fail because something goes wrong. It fails because gravity works too well. The collapse happens so smoothly that light never gets the chance to escape. This makes these black holes very hard to find. There is no explosion to trace back, no expanding cloud of gas, no clear birth record. Scientists only notice something is missing. A star that was once there is suddenly gone. That absence becomes the clue. One of the strange parts is how fast this happens. The final collapse can take less than a second. A star that existed for millions of years ends without noise or warning. From the outside universe, it looks like nothing happened at all. This means the universe may be filled with black holes that were never announced. They formed without drama. No light, no sound, just gravity closing in and leaving behind something invisible yet powerful where a star used to be. Right after the universe began, everything was different from what we see today. Space, time, and energy were packed into a tiny, dense state. Temperatures were unimaginably high, and matter as we know it could not exist. Most of the universe was a hot, chaotic soup of particles moving at extreme speeds. Yet even in this chaos, black holes may have been born. These are called primordial black holes. They are not formed from stars because there were no stars yet. Instead, they could form wherever matter was unevenly packed. If a small region had slightly more mass than its surroundings, gravity could pull it together so strongly that it collapsed immediately into a black hole. This could happen in less than a second after the Big Bang. Imagine a tiny spot in the universe becoming so dense that nothing, not even light, could escape. Primordial black holes are strange because they are different from the black holes we usually think about. They can be much smaller than the black holes formed from stars, sometimes just the size of a mountain. But even at that small size, the gravity around them is extreme. A particle passing nearby would be trapped instantly. They might also exist in huge numbers, scattered through space, hiding from our view because they do not emit light. Scientists are especially interested in these early black holes because they could explain mysteries about the universe. Some believe they might have influenced how galaxies formed. Others think they could even account for some of the invisible matter called dark matter. If these tiny black holes still exist today, they could be anywhere, quietly shaping the cosmos. Even more curious, some of these black holes might have evaporated over billions of years, shrinking due to processes we are only beginning to understand. That means the universe once had more of them than it does now, and what remains is just a hint of the extreme conditions that existed at the very beginning. The idea that a black hole could form before any star or galaxy existed shows how gravity works under the most unusual circumstances. It is a reminder that the universe can create something invisible and powerful even in its first moments, silently shaping everything that comes after. A black hole is not just a simple point in space. While its core, the singularity, is extremely dense and tiny, the black hole also has a boundary called the event horizon. This is the point where nothing can escape, not even light. But here's something most people don't realize. The size of this boundary is not fixed. It changes depending on how fast the black hole is spinning. Black holes can rotate, and some spin at incredible speeds. This rotation stretches the space around them in strange ways. Imagine space itself being twisted along with the black hole. Because of this, the event horizon is no longer a perfect sphere. It becomes slightly flattened at the poles and wider at the middle. The faster the spin, the more the boundary stretches outward along the equator. A black hole spinning close to its maximum speed can have an event horizon that is significantly larger in some directions compared to a non-spinning one of the same mass. The spinning also creates another unusual region outside the event horizon called the ergosphere. Here, space is dragged along with the black hole's rotation. Objects entering this region can still escape, but they are forced to move in the direction of the spin. This makes the space around spinning black holes dynamic, almost like it's alive, moving with the object at its center. The faster it spins, the stronger this effect becomes. This means that two black holes with the same mass can have very different sizes in terms of their influence on nearby space, depending on their spin. Observing the difference is challenging, but scientists can detect it by studying how matter moves in the black hole's surroundings, such as in the accretion disk or jets. Faster spins tend to create more energetic jets and change the paths of orbiting matter. The key idea is that a black hole's size is not a single, fixed number. It is a result of mass combined with motion. Spin stretches space, changes the boundary, and even affects how nearby matter behaves. In this way, each black hole is unique, shaped not just by how much it weighs, but by how fast it turns, making the universe even stranger and more fascinating than it appears. A black hole might seem like a permanent, unchanging object, but its boundary, the event horizon, is actually very sensitive. Even the smallest change in the black hole's mass can make this invisible boundary grow or shrink. This is surprising because we often imagine black holes as enormous, unmovable objects that swallow everything and never change. In reality, they are more dynamic than most people realize. The event horizon marks the point of no return. Anything that crosses it, whether light or matter, cannot escape. Its size depends directly on the black hole's mass. If the black hole gains even a tiny amount of matter, the event horizon expands slightly. This can happen when a small asteroid, a cloud of gas, or even a stray particle falls in. The increase may be almost impossible to detect, but the boundary responds instantly to the added mass. On the other hand, black holes can also lose mass. They emit something called Hawking radiation, a process predicted by Stephen Hawking. Although the amount of energy lost this way is extremely small, over billions of years it can shrink the black hole. Even this tiny reduction causes the event horizon to contract. This means the boundary is never fixed, constantly adjusting based on what the black hole gains or loses. The change in the event horizon can also affect nearby space. If the black hole grows, the area where gravity dominates expands, altering the orbits of objects that were previously safe. If it shrinks, objects that were just outside the boundary remain outside, but the balance of forces around them changes subtly. This responsiveness shows that black holes are not static traps, but active participants in the cosmic environment. They are sensitive to tiny influences, reacting to the addition or loss of even the smallest particles. The idea that such a massive object can respond to almost invisible changes challenges our intuition. Black holes are extreme, yet delicate in a way, constantly reshaping the invisible lines that define them. They are powerful, silent, and surprisingly flexible, adjusting to the universe around them in ways most people never notice. One of the strangest things about black holes is how they appear to behave from far away. If you watch an object fall toward a black hole, like a piece of dust, a spaceship, or even a stream of gas, it never seems to cross the event horizon. Instead, it appears to slow down more and more as it gets closer, taking forever to actually reach the point of no return. To an observer far away, it's as if the matter is frozen in time, stuck at the edge of the black hole. This happens because of how gravity affects time. Near a black hole, gravity is so strong that it stretches time itself. The closer something gets to the event horizon, the slower time passes for it compared to someone far away. From your point of view outside the black hole, the falling object moves slower and slower, eventually fading as its light stretches into longer and longer wavelengths. It never seems to disappear completely, but instead appears redder and dimmer, like it is frozen on the edge of space. For the object falling in, the experience is completely different. It would cross the event horizon in a finite amount of time, without noticing any sudden barrier. But because light cannot escape once it passes the horizon, anyone watching from the outside can never see it fully enter. The black hole creates this strange illusion, where the universe outside seems frozen while the interior unfolds normally for the falling matter. This effect makes black holes even more mysterious. They are places where the rules of observation and reality do not match. What you see from a distance is not what is happening locally. Scientists have to rely on indirect signals, like radiation from matter orbiting the black hole or gravitational waves from merging black holes, to understand what is really happening inside. It is a reminder that black holes are not just objects in space, but distortions of time and observation itself. They hide what is happening within them, creating a natural boundary that looks eternal from afar. What seems frozen at the edge is actually moving, collapsing, and changing, but the black hole keeps its secrets perfectly hidden from the outside universe. When two black holes collide, the result is far more than a bigger black hole. The event sets the fabric of space itself vibrating in a way that is both subtle and powerful. Scientists have discovered that black holes can actually ring after merging, creating ripples that travel across the universe. These vibrations are called gravitational waves, and they are like echoes of the violent cosmic collision. Imagine two black holes spiraling toward each other. As they get closer, their gravity pulls and twists space around them, causing both to move faster and faster. When they finally collide, the newly formed black hole is not perfectly smooth. Its shape is distorted, stretched and compressed in different directions. Just like a bell that has been struck, it oscillates as it settles into a stable form. These oscillations create gravitational waves that spread outward at the speed of light, carrying information about the collision across billions of light years. Unlike sound waves, these ripples are invisible and do not travel through air. Instead, they are distortions in spacetime itself, stretching and squeezing distances between objects as they pass. The waves are extremely weak by the time they reach Earth, but with sensitive instruments like LIGO and Virgo, scientists can detect them. Each wave provides a record of the collision, revealing the mass, spin, and energy of the black holes involved. In a way, the universe itself has recorded the sound of two black holes ringing, and we are listening billions of years later. The ringing is not constant. It fades quickly as the black hole stabilizes, but during that brief moment, it sends out measurable echoes. These echoes are the only direct evidence we have of black holes merging and confirm predictions made by Einstein's theory of general relativity over a century ago. What makes this even stranger is that each black hole merger produces a unique pattern, like a fingerprint. No two collisions ring in exactly the same way. By studying these spacetime echoes, scientists can learn about black holes that cannot be seen directly. It is as if the universe allows us to hear its most extreme events, revealing secrets of cosmic objects that would otherwise remain completely hidden. Black holes, silent in light, are speaking in vibrations, and we have learned how to listen. Two black holes can interact in ways that seem almost impossible. Instead of immediately colliding when they meet, they can orbit each other for millions of years. They circle around a shared center, locked in a gravitational dance that is stable but constantly changing. Each black hole pulls on the other, and their motion warps the space around them. From a distance, this looks like two invisible points tracing a slow, endless path, while the universe continues around them. The orbit is not always simple. Depending on their mass, speed, and distance, the path can be elliptical, meaning one black hole moves closer and farther from its partner repeatedly. As they orbit, they emit tiny ripples in spacetime called gravitational waves. These waves carry energy away, even if it is incredibly small at first. Over millions of years, the energy loss slowly brings the black holes closer together, tightening their orbit. This process is extremely slow compared to human time, but in cosmic terms, it is the prelude to one of the most dramatic events in the universe. The final merger is sudden compared to the long orbit. After millions of years circling each other, the black holes spiral inward rapidly, colliding to form a single, larger black hole. When this happens, the gravitational waves grow stronger, sending a brief but intense signal across the cosmos. Scientists on Earth can detect these signals, and each one tells a story about the black hole's mass, spin, and the speed of their final collision. What is fascinating is that during the long orbit, the black holes are mostly invisible. They might be surrounded by gas or stars, but the black holes themselves emit no light. For millions of years, they circle in silence, shaping their surroundings purely through gravity. Only at the very end does the universe notice the collision through gravitational waves. This long dance shows how patient and precise nature can be. Black holes are not always violent immediately. They can interact for eons in ways that are orderly and predictable. Their slow orbit and eventual merger give scientists a window into extreme physics and the workings of gravity, revealing patterns and behaviors that are almost impossible to imagine. Even in silence, black holes leave traces that the universe can record and, eventually, we can observe. A black hole does not need to swallow matter to have an effect on its surroundings. Some black holes spin at incredible speeds, and their rotation alone can extract energy from the space around them. This is not a form of suction or pulling in matter, but a more subtle and surprising effect of gravity and motion combined. The faster a black hole spins, the more it can influence everything nearby. The process begins with the area just outside the black hole, called the ergosphere. In this region, Space itself is dragged along with the black hole's rotation. Objects entering this zone are forced to move in the direction of the spin, even if they try to resist. This effect allows energy to be transferred from the black hole to anything within the ergosphere. Essentially, the black hole is twisting space and extracting energy from that motion. Scientists have shown that this energy can be tapped in theory. If a particle enters the ergosphere in a particular way, it can leave with more energy than it entered with. The extra energy comes directly from the black hole's spin. Over time, this slows the rotation slightly, converting the black hole's motion into usable energy for its surroundings. It is like a cosmic machine, spinning silently and transferring power without consuming mass. This energy transfer is thought to power some of the universe's most extreme phenomena. High-speed jets shooting out from black holes at nearly the speed of light may originate from this mechanism. The black hole's spin twists magnetic fields in the surrounding plasma, accelerating particles and launching them across vast distances. All of this happens without the black hole directly eating the matter producing the jets. What makes this fascinating is that a black hole, which seems like a purely destructive object, can instead act as a source of energy through rotation. It highlights how gravity is not just a force of attraction, but a way to manipulate motion and energy on a cosmic scale. Even in the emptiest regions of space, a spinning black hole can reach out invisibly, transferring power and shaping its surroundings, silently altering the universe without touching a single particle directly. Not all black holes stay in one place. Some are moving through space at astonishing speeds, thousands of kilometers per second. To put that into perspective, that is faster than most stars in our galaxy, and even faster than many spacecraft could ever hope to travel. These black holes are not tied to a single system or galaxy. They are cosmic wanderers, carrying immense mass as they move silently through the universe. How does a black hole reach such speed? One way is through violent cosmic events. When two massive stars in a binary system explode, they can leave behind black holes with a strong kick. The force from the explosion pushes the black hole, sending it hurtling into space. Another way is when a black hole is ejected from the center of a galaxy during a collision with another black hole. In these cases, the black hole can escape its home entirely, becoming a solitary traveler. Despite their incredible speed, moving black holes are almost impossible to detect. They do not emit light, and their gravity is invisible unless something comes very close. Scientists can sometimes spot them by observing how they affect nearby stars or gas clouds, or by detecting X-rays if the black hole pulls in matter along its path. Even then, finding one is like spotting a needle in a cosmic haystack. The idea that black holes can move so fast changes how we think about them. They are not always fixed at the centers of galaxies. Some can roam the vast spaces between galaxies for millions or even billions of years, completely unseen. Their motion can subtly influence stars and gas they pass by, bending or pulling on nearby matter purely with their gravity. This also raises questions about the history of the universe. Each moving black hole carries evidence of the violent events that created it. By studying them, scientists can reconstruct ancient supernovae, collisions, and mergers that happened long before humans existed. In a way, these traveling black holes are silent messengers, moving at impossible speeds while holding secrets of the universe's past, quietly shaping everything around them without anyone noticing. Not all black holes stay within galaxies. Some may be wandering alone in the vast space between galaxies, with no stars, planets, or gas clouds nearby. These black holes are invisible in the traditional sense because they emit no light, and without nearby matter to interact with, they leave almost no trace. They are like cosmic ghosts, silently moving through the emptiness, far from anything familiar. How do these lonely black holes form? One way is through galaxy collisions. When two galaxies merge, their central black holes may interact violently. One can be ejected from the newly formed galaxy entirely, sent flying into intergalactic space at incredible speeds. Another possibility is smaller black holes, formed from the collapse of stars in galaxies, may be flung out by gravitational interactions or close encounters with other massive objects. Over billions of years, these black holes can end up far from any stellar system, wandering alone. Detecting these objects is extremely challenging. Without stars or gas to light up their presence, astronomers cannot see them directly. Instead, they look for indirect evidence, like tiny gravitational effects on passing stars or gas clouds, or rare moments when a black hole happens to capture matter. Even a single cloud of gas falling into a rogue black hole could produce X-rays strong enough to signal its location. The existence of these wandering black holes changes how we understand the universe. Space is not just filled with galaxies and stars. It may also contain countless invisible travelers, moving silently in the void. Some of these black holes might be relatively small, while others could be massive, carrying the remnants of ancient galactic centers. This idea also raises questions about cosmic history. Each wandering black hole is a clue to past events, explosions, collisions, and mergers that happened billions of years ago. Even in isolation, they have the power to shape anything they encounter. A passing black hole could influence nearby star systems or gas clouds, altering their paths and triggering events far from its original home. In a way, these lonely black holes are reminders of how dynamic the universe is. Even empty space is not truly empty. Invisible forces move silently across the cosmos, shaping the universe in ways we can barely detect. Yet their presence is real, powerful, and endlessly fascinating. When most people imagine a black hole, they think of a single, infinitely small point called a singularity at its center. This is where all the mass is thought to be concentrated, and where gravity becomes infinitely strong. But in reality, the center of a black hole is not guaranteed to be a single point. Its true structure may be far more complex than we can easily picture. The original idea of a singularity comes from equations in general relativity. According to these equations, under normal conditions, gravity compresses all the matter into an infinitely dense point. However, these equations break down under extreme circumstances. They cannot fully describe what happens when quantum effects, which govern the smallest particles, interact with such intense gravity. This means the point might not exist as we imagine it. Some theories suggest that the center could be spread out into a tiny sphere or even a ring, especially if the black hole is spinning. A rotating black hole may form a ring-shaped singularity instead of a point, where the mass is concentrated in a circular shape. This changes how space behaves near the core. The gravity near a ring singularity is extremely strong, but it is not the same in every direction, creating unique effects on anything falling toward it. Other ideas propose that the center could have a structure we cannot yet observe or understand, hidden by the event horizon. It might be a dense but finite region instead of an infinitely small point. Quantum physics may prevent the formation of a true singularity, spreading the mass over an extremely small but measurable volume. This uncertainty is important because it shows that black holes are still one of the least understood objects in the universe. The center, where gravity is at its strongest, may not behave the way our equations predict. Scientists are studying indirect effects, such as gravitational waves and the motion of matter near black holes, to learn more about what really exists at the core. The idea that the center might not be a point challenges everything we think about matter and gravity. It suggests that even the most extreme objects in the universe may have hidden structures, waiting for us to understand. Black holes are not only powerful and mysterious, but they also reveal the limits of our knowledge and the strange possibilities that lie at the heart of space itself. Black holes are often described as having a point at their center, but the reality may be far stranger. Some equations in physics allow for singularities that are not points at all. Instead, they could take the shape of a ring or be distorted into unusual forms, depending on how the black hole spins and how it formed. These possibilities are surprising because they challenge the idea that all mass in a black hole is concentrated in a single location. A rotating black hole, for example, can produce a ring-shaped singularity. When a black hole spins, it twists the space around it, stretching and flattening the core. The mass is still concentrated in a very small region, but instead of a single point, it forms a ring. This shape affects how objects fall toward the black hole. Near the ring, gravity behaves differently in different directions, creating paths that would be impossible around a simple point singularity. Equations also allow for more distorted singularities under extreme conditions. For instance, a black hole that formed from an irregular collapse of matter or from merging with another black hole may not be symmetrical. Its core could be stretched, compressed, or warped in unusual ways. These distortions would influence the black hole's gravitational field, changing how matter and light move around it. Even though we cannot see these singularities directly, scientists can study their effects. Gravitational waves from black hole mergers, the behavior of matter in accretion disks, and simulations using Einstein's equations give clues about the possible shapes. Each observation adds to our understanding and hints that the simple point at the center model is incomplete. The idea of ring-shaped or distorted singularities shows that black holes are not just extreme. They are flexible in ways we don't normally expect. The laws of physics allow for structures that challenge our intuition, reminding us that the universe can behave in ways that are counterintuitive. At the center of a black hole, space and gravity may twist into forms we cannot imagine, creating realities that exist beyond ordinary experience, hidden behind the event horizon but influencing the cosmos in profound ways. Time behaves in ways that seem impossible near a black hole. The closer you get to one, the stronger its gravity becomes, and that gravity actually changes the flow of time. This effect is called time dilation. From a distance, the universe follows its normal pace. But near a black hole, time slows down dramatically. Seconds for someone close to the black hole could equal years for someone far away. Imagine an astronaut hovering near the edge of a black hole just outside the event horizon. For them, life would feel normal. They could move, breathe, and think as usual. But if they could look back at Earth, they would see events speeding by. Days would turn into months in what feels like seconds near the black hole. People on Earth would age much faster, while the astronaut remains almost frozen in time. This effect becomes extreme at the edge of the event horizon. Theoretically, if you could hover there without being pulled in, the rest of the universe could age billions of years in the time it takes you to experience a few hours. This is not science fiction. It is a real prediction from Einstein's theory of general relativity. Gravity is so strong that it warps both space and time, creating a situation where the universe outside the black hole behaves on a completely different clock. Time dilation also explains why matter falling into a black hole appears frozen to an outside observer. From far away, the object slows down, never seeming to cross the event horizon. Meanwhile, locally, the falling object experiences time normally. The The two perspectives are both true, showing how flexible and strange time can be under extreme gravity. The fact that time can slow near a black hole makes these objects even more mysterious. They are not just dense regions of space. They are regions where the universe itself bends and stretches, altering reality in fundamental ways. Near a black hole, the normal flow of life is suspended, and the rest of the cosmos races ahead. This shows that black holes do not just influence space, they manipulate time itself, creating environments where the ordinary rules of experience no longer apply. Falling into a black hole might sound terrifying, but the experience depends greatly on the size of the black hole. For very large black holes, the effects of gravity near the edge can be surprisingly gentle at first. The tidal forces, which stretch objects as they approach, are much weaker near a supermassive black hole than they are near a smaller one. This means that an object or person falling in could feel almost normal for a long time. Imagine approaching a black hole with billions of times the mass of the sun. From far away, it appears as a dark sphere in space. As you move closer, gravity becomes stronger, but in a very gradual way. Unlike smaller black holes, there is no immediate spaghettification, the stretching and squeezing caused by intense gravity. You could cross a significant portion of the black hole's outer region without noticing any extreme forces acting on your body. Time and motion would feel ordinary, and the sky around you would still look familiar. This slow, almost undetectable approach continues until you get much closer to the event horizon. At that point, gravity increases sharply, and the stretching begins. But for a supermassive black hole, this transition happens gradually enough that you have time to observe the surrounding universe, see light bend in unusual ways, and notice the distortion of space before being pulled fully inward. For an outside observer, the experience looks very different. They would see you slowing down as you approach the black hole, appearing frozen near the event horizon. But locally, you would continue moving as usual, with nothing immediately unusual happening. This difference between local and distant perspectives highlights how extreme gravity warps time and space. The fact that falling into a large black hole can feel normal at first challenges our common ideas about these objects. They are not always violent traps waiting to tear everything apart instantly. In some cases, they allow for extended observation of the strange physics near their boundaries. This delay before the real effects take hold makes supermassive black holes unique, offering a quiet, almost deceptive entry into one of the universe's most extreme environments. Black holes have a power that most people cannot even imagine. They can bend light itself. Gravity is not just a force that pulls objects, it also curves the space around it. Light, which normally travels in straight lines, follows the curves of space. Near a black hole, these curves can be so extreme that light can travel in complete circles, looping around the black hole multiple times before continuing on its path. This effect is called gravitational lensing. When light from a star or galaxy passes near a black hole, it does not move straight to an observer. Instead, the black hole's gravity bends it. In some cases, light can circle the black hole several times, creating multiple images of the same object. From far away, it might look like there are several stars in different places, when in reality it is just one, repeated by the bending of space. The most extreme example of this is called the photon sphere. This is a region just outside the event horizon, where gravity is strong enough to force light into a circular orbit. Photons, the particles of light, can theoretically circle the black hole indefinitely. Of course, any disturbance or tiny shift will eventually send the light outward or inward, but for a brief moment, light can orbit, creating strange and almost impossible patterns for distant observers to see. Gravitational lensing is more than just a curiosity. Scientists use it to study black holes and distant galaxies. By analyzing how light bends around massive objects, they can map the shape and mass of black holes, even if the black hole itself cannot be seen. Some images captured by telescopes reveal arcs, rings, or duplicated stars caused entirely by this effect. This phenomenon shows how black holes distort reality. Space and light are no longer predictable in their usual ways. Light can loop, twist, and create multiple versions of the same object, proving that black holes do not just pull, they reshape the paths of everything near them. In the presence of a black hole, what you see may not be real at all, but an echo of the universe bending around a point of unimaginable gravity. Black holes are invisible, but they can reveal distant parts of the universe in surprising ways. Their intense gravity can act like a cosmic magnifying glass, bending and focusing light from stars or galaxies that are far behind them. This effect allows distant objects to appear brighter and larger, even though the black hole itself remains hidden from view. This happens because of gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. When light passes near a black hole, the path of the light bends toward the black hole. If a star or galaxy is lined up behind it, the light can be focused and stretched, forming arcs, rings, or multiple images. Observers on Earth may see these magnified images without ever seeing the black hole that caused them. In a way, the black hole acts like an invisible lens, reshaping the light in ways that can reveal details of the universe we would otherwise miss. Scientists use this effect to study extremely distant objects. Some galaxies are so far away that their light is very faint and hard to observe. If a black hole happens to be between us and the galaxy, the bending of light can amplify its brightness, making it visible through telescopes. This method has helped astronomers discover and study parts of the universe that are billions of light years away. Even more surprising, the black hole does not need to consume anything to create this effect. It is purely the warping of space and light that produces the magnification. While the black hole itself remains completely dark, it allows distant light to travel in unusual paths, creating multiple or stretched images of objects that could never be seen otherwise. This ability of black holes to magnify the universe shows that they are not just destructive forces. They are also tools that reveal hidden parts of space, altering how we perceive what is far away. By bending and focusing light, black holes let us see the invisible, quietly shaping our understanding of the cosmos without ever revealing themselves. They are like invisible windows into the distant universe, powerful, hidden, and strangely helpful. Black holes are often thought of as loud, violent objects, swallowing stars and blasting out energy. But some black holes are quieter than the empty space around them. They do not emit light, heat, or jets, and they interact so subtly with their surroundings that detecting them is extremely difficult. In some regions of space, these black holes may appear to be completely silent, almost like nothing is there at all. The quietness depends on what the black hole is doing, or not doing. Many black holes become visible only when they are actively pulling in matter. Gas, dust, or nearby stars can heat up as they spiral in, releasing X-rays or other forms of energy. But if there is no matter nearby, a black hole can remain perfectly invisible. It is massive and powerful, yet it produces no detectable signals. In that sense, it can be quieter than the vacuum of space itself, which is filled with cosmic background radiation and particles moving through it. These silent black holes may be wandering alone in interstellar or intergalactic space, far from any stars or galaxies. They carry all their mass and gravity with them, yet they leave almost no trace. Even if a spacecraft or a planet passed nearby, the effects would only be detectable through precise measurements of gravitational influence. Otherwise, these black holes remain hidden, quiet, and largely unknown. Detecting them requires indirect observation. Scientists look for subtle movements in stars or gas that suggest a massive object is present. Sometimes, gravitational lensing, the bending of light, can reveal a black hole's presence. Even then, the signals are faint, and many such black holes may exist in the universe without our knowledge. The idea that a black hole can be quieter than empty space challenges our intuition. We often imagine them as destructive monsters, but some exist in near-perfect stillness. Their silence reminds us that the universe contains extremes in every direction, not just violent chaos, but also invisible, silent forces shaping the cosmos quietly. These hidden black holes are among the most mysterious objects in existence, influencing space without making a sound. Matter behaves in strange ways near a black hole, and one surprising fact is that it can orbit much closer than most people expect. Usually, we imagine that anything near a black hole is doomed to be pulled in immediately. But under the right conditions, gas, dust, or even stars can maintain a stable orbit extremely close to the event horizon, circling the black hole without falling in. This happens because of the balance between two forces. Gravity is pulling everything inward, trying to drag matter into the black hole. At the same time, matter moving sideways at high speeds creates an outward effect, a kind of centrifugal force that keeps it from collapsing. When these two forces balance perfectly, matter can remain in orbit. For very large black holes, this stable region can exist closer than we would normally expect, where gravity is extremely strong. One famous example is the innermost stable circular orbit, or ISCO. This is the closest distance where matter can orbit without falling in. For spinning black holes, this orbit can be even closer than for non-spinning ones. The faster the spin, the more space near the black hole is flattened and twisted, allowing matter to circle almost at the edge of the event horizon while remaining stable. This phenomenon has practical consequences for astronomers. The inner edge of an accretion disk, the bright swirling matter around a black hole, is determined by this stable orbit. Matter in this region moves at enormous speeds, sometimes a significant fraction of the speed of light, creating intense radiation that we can detect from Earth. Observing these disks allows scientists to measure the spin and mass of black holes indirectly. The fact that matter can orbit so close challenges the idea that black holes are simple, all-consuming traps. They are more like extreme laboratories of motion, where the rules of gravity and inertia create unexpected stability in conditions that would destroy ordinary objects. Near a black hole, matter can survive in what seems like impossible positions, circling silently and perfectly balanced, showing that even in the most extreme parts of the universe, order can exist alongside chaos. Once an object crosses the event horizon of a black hole, the rules of space and direction change completely. Outside, we think of moving forward, backward, left, or right as simple choices. Inside a black hole, these familiar directions lose their meaning. All paths, including what feels like forward, lead toward the center, the singularity. There is no escape. No matter which way you try to go, you are drawn inevitably inward. This happens because gravity inside a black hole warps space and time to an extreme degree. Space itself is stretched so that the center is not just a point you fall toward. It becomes the only direction you can move. From the moment you cross the event horizon, moving away from the center is impossible, no matter what you do. Even light, which normally travels straight unless bent by gravity, is forced inward. Every direction, every attempt to move, eventually leads closer to the singularity. To an observer falling in, this change might feel subtle at first. Time and movement continue normally at first, but no choice can avoid the inward pull. Outside observers, however, would see you slow down and freeze near the event horizon, never actually crossing it from their point of view. Inside, reality is completely different. Space itself guides every step toward the center. This strange property is part of what makes black holes unique in the universe. They are not just massive objects that pull things in. They are regions where the structure of space and time is fundamentally altered. The rules that normally govern motion and direction no longer apply. Instead, the singularity at the center dictates the path for everything inside the event horizon. Understanding this helps explain why nothing can escape a black hole. It is not just gravity acting like a strong force. It is space itself bending to make escape impossible. Every object, from particles to light beams, is carried inward. Crossing the event horizon is the point of no return, not because of friction or force, but because the very directions of motion inside have been rewritten, all pointing inevitably to the center. Black holes are invisible, so you might think it is impossible to measure their mass. Yet astronomers have found clever ways to calculate how heavy a black hole is without anything ever touching it. The key is to watch how nearby stars or gas move under the black hole's gravity. Even if the stars never get close enough to be swallowed, their paths reveal everything we need to know. Stars orbiting a black hole behave like planets orbiting a sun, but with much stronger gravity. By carefully tracking the speed and path of these stars, scientists can determine the mass of the invisible object controlling their motion. Faster or tighter orbits indicate a heavier black hole, while slower, wider orbits suggest a lighter one. With modern telescopes and long-term observations, these tiny changes in motion can be measured with incredible precision. This method has been used to discover supermassive black holes at the centers of galaxies, including our own Milky Way. Stars very close to the galactic center orbit something massive and invisible. By calculating their paths, scientists have determined that the mass concentrated there is millions of times the mass of the Sun. The stars themselves never touch the black hole. They orbit safely outside the event horizon, but their motion tells the full story. Even smaller black holes can be measured in the same way if they have nearby stars or gas. X-ray emissions from hot gas swirling around a black hole also provide clues about its mass. By combining these observations with the motion of orbiting stars, astronomers can build an accurate picture of an object that cannot be seen directly. This ability shows how black holes influence the universe even without visible signs. Their gravity leaves measurable effects on everything around them, allowing scientists to study something that cannot be observed with light. By watching stars move, we can weigh the invisible, proving that black holes, though unseen, are real, powerful, and measurable objects shaping the cosmos from afar. Black holes are famous for hiding everything they swallow, but recent ideas in physics suggest that information may not be lost inside them at all. Instead, it could be encoded on their surface, the event horizon. This is one of the strangest concepts in modern science because it challenges the way we think about space, matter, and information. The idea comes from the holographic principle. According to this, all the information about the matter that falls into a black hole, its mass, charge, and other properties, might be stored on the event horizon itself, like a two-dimensional record of a three-dimensional object. Nothing actually stays inside the black hole in the traditional sense. Instead, the surface of the black hole acts like a cosmic screen, storing details about everything that has ever crossed the boundary. This could solve a long-standing problem in physics. For decades, scientists wondered if black holes destroy information, which would violate fundamental rules of quantum mechanics. If all the information is stored on the surface, it is never truly lost. Even if the black hole eventually evaporates through Hawking radiation, the information might be preserved in subtle ways, encoded in the radiation emitted. The concept is difficult to imagine because it goes against normal experience. In everyday life, information is usually stored inside objects. A book contains words written on its pages, and a computer stores data inside its circuits. But a black hole turns this upside down. The information is on the boundary, not inside. It suggests that reality at the smallest scales may work very differently from what we see around us. Scientists are still exploring how this principle works and how information could be read from a black hole's surface. Experiments are impossible for now, but theoretical models continue to support the idea. If true, it shows that black holes are not just destructive, they are also record keepers of the universe. Even in darkness, they may preserve the history of everything that comes near, silently storing the secrets of matter on their surfaces in ways we are only beginning to understand. Black holes have properties that seem to defy common sense, and one of the most surprising is how their surface area behaves. The surface, called the event horizon, never decreases, even when the black hole loses mass or shrinks. This idea comes from a connection between black holes and the laws of physics, particularly a relationship similar to the second law of thermodynamics, which states that the total disorder, or entropy, of a system never decreases. When a black hole absorbs matter, its mass increases, and its event horizon expands. This makes sense. More mass means stronger gravity, which stretches the boundary outward. But even when a black hole loses mass, for example through Hawking radiation, the situation is more subtle. The black hole emits energy in the form of particles, and as it shrinks, the energy radiated ensures that the overall surface area of the event horizon, when considered in the correct theoretical sense, never decreases. In other words, the black hole cannot shrink in a way that reduces this cosmic surface below its previous maximum. This property is surprising because we usually think of shrinking objects as losing size in all directions. But black holes do not follow ordinary rules. The event horizon is not just a physical surface. It is also tied to the information and entropy of the black hole. The area represents the total amount of information that could be encoded on the surface, and this must always stay the same or grow. Anything that falls in increases the area, while evaporation or energy release cannot reduce it below the existing limit. This concept also helps scientists understand black holes in terms of thermodynamics and quantum physics. It suggests a deep link between gravity, energy, and information, showing that black holes are not only massive objects, but also objects with measurable laws, similar to temperature and entropy. In short, even when a black hole appears to shrink, its surface area never truly decreases. This challenges our everyday intuition about size and shape. Black holes are governed by strange rules that combine gravity, energy, and information, creating a universe where the boundaries of objects are more than just physical. They are reflections of deeper cosmic laws. Black holes are often imagined as objects that only grow by swallowing matter, but they can also slowly lose mass over time. This process is called black hole evaporation. Surprisingly, this happens without any light, sound, or obvious signals. It is a quiet, almost invisible process, unlike the violent images most people associate with black holes. The evaporation occurs through something called Hawking radiation, a concept proposed by physicist Stephen Hawking. In the strange world of quantum physics, empty space is not truly empty. Tiny particle pairs constantly appear and disappear everywhere, even near a black hole. Occasionally, one of these particles falls into the black hole while the other escapes. The escaping particle carries away a tiny amount of energy, which effectively reduces the mass of the black hole. This process is extremely slow for large black holes. A black hole with the mass of the Sun would take longer than the age of the universe to evaporate completely. That's why, in most cases, black holes appear permanent and unchanging. The loss of mass is so subtle that it produces no light or sound detectable by ordinary means. The black hole remains silent, continuing to bend space and influence its surroundings while shrinking imperceptibly. As the black hole loses mass, its event horizon slowly shrinks, but the process still follows the rules of physics. Even without emitting visible signals, the black hole is gradually releasing energy back into the universe. This energy is carried by the escaping particles and contributes to the overall energy balance of space. Hawking radiation shows that black holes are not completely eternal. They are dynamic objects that can interact with the universe in ways we cannot see directly. Unlike explosions or collisions, this evaporation is a quiet reminder that even the most extreme objects are not entirely permanent. The universe contains subtle mechanisms like this, where enormous power is released invisibly, and black holes slowly change over time without making a sound or showing light. It is a quiet, invisible form of cosmic transformation, almost like the universe is aging silently around these mysterious objects. Black holes can live for incredibly long periods, but their final moments are astonishingly different. As a black hole slowly loses mass through Hawking radiation, the process speeds up dramatically near the end. While it may have existed for billions or even trillions of years, the last stage of evaporation could happen in a tiny fraction of that time. This sudden acceleration makes the end of a black hole's life one of the most extreme events in the universe. The reason for this rapid final stage lies in the relationship between a black hole's mass and its temperature. Large black holes are extremely cold and emit very little Hawking radiation, so they shrink very slowly. But as the black hole loses mass, it becomes hotter, emitting more radiation and losing mass faster. This creates a feedback loop. Smaller mass leads to higher temperature, which leads to more radiation, which further reduces the mass. Eventually, this process becomes extremely fast, meaning the black hole could vanish almost instantaneously compared to its long history. For an outside observer, this final evaporation would appear sudden and violent, even though the black hole itself produces no light or sound in a traditional sense. The energy is released as tiny particles, and the black hole disappears completely, leaving behind only the effects it had on the surrounding space. Scientists call this a black hole explosion, though it is very different from a supernova. It is an invisible, high-energy release, unlike anything we experience in daily life. This rapid end also highlights the strange nature of time and scale near black holes. Something that took billions of years to shrink slowly can end in seconds or less, showing how extreme gravity and quantum effects interact. The black hole's long history collapses into an almost instantaneous event, reminding us that the universe operates under rules that often defy our normal intuition. The idea that a black hole's last moments could outpace its entire lifetime is both thrilling and puzzling. It shows that even the largest, most stable objects in the universe are temporary, and their endings can be as dramatic as their long, quiet existence. The universe is full of extremes, and black holes demonstrate this more than almost anything else. Not all black holes are enormous and dangerous. Some may be tiny, with masses far smaller than the Sun, and if one of these microscopic black holes existed, it could, in theory, pass through Earth without anyone noticing. Unlike the massive black holes at the centers of galaxies, these tiny ones have extremely weak gravitational effects on objects around them. They would be nearly impossible to detect with ordinary instruments. The reason a tiny black hole could pass through Earth unnoticed is that its size and mass are so small. While it is still dense and powerful in theory, the distance between atoms in matter is vast compared to the size of a microscopic black hole. As it moves, it would pull on nearby matter extremely weakly, barely affecting anything in its path. People, buildings, and the planet itself would not feel it. It could pass straight through the Earth, entering one side and exiting the other without causing an earthquake, explosion, or any noticeable gravitational effect. Of course, a black hole of this size is extremely hypothetical. Scientists have considered the possibility that tiny black holes could form naturally in the early universe or even be created in high-energy experiments, but none have been observed. If one existed, it would be so small that its event horizon, the boundary beyond which nothing can escape, would be smaller than an atom. The black hole would not swallow anything in the usual sense. It would simply pass through matter, interacting only very slightly with the particles it encounters. Even though this sounds like science fiction, it highlights how strange black holes can be. Size does not always correlate with danger. The universe could contain countless tiny black holes that are quietly moving through space, completely invisible and harmless to planets, stars, or people. The idea of a tiny black hole passing through Earth challenges our imagination. It shows that black holes are not only massive cosmic monsters but also subtle, almost ghost-like objects. Some of the most extreme physics in the universe could occur right under our feet, or through our planet, without anyone ever knowing. Black holes can be both terrifyingly powerful and completely undetectable, depending on their size, reminding us how strange and mysterious the cosmos truly is. Black holes have a reputation for sucking everything nearby, but this is actually a misconception. They do not pull objects in like a vacuum cleaner. Gravity works differently. A black hole's gravity is strong, yes, but it only attracts objects that are already moving toward it or are within its gravitational reach. Objects that are far away and moving in the right path can orbit safely without ever being pulled in. Imagine the Sun replaced by a black hole of the same mass. The planets, including Earth, would continue orbiting just as they do now. The black hole's gravity at that distance is exactly the same as the Sun's. Nothing would suddenly get sucked in. For a black hole to capture an object, the object has to move toward it, or its orbit must bring it close enough that gravity overcomes its momentum. Otherwise, it continues on its usual path through space. This is why many black holes can exist in space quietly, without consuming nearby stars immediately. Matter only falls in when it is in a trajectory that leads to the event horizon, or if it is captured in an accretion disk, a swirling ring of gas and dust slowly spiraling inward. The black hole itself is not actively pulling things from far away. The matter must already be moving in a way that allows gravity to take over. Understanding this helps remove some of the fear and mystery surrounding black holes. They are not cosmic vacuum cleaners randomly sucking everything in. Their effect is entirely based on gravitational pull, motion, and proximity. Objects can orbit or pass by safely, even very close to a black hole, if they have the right speed and direction. This also explains why black holes can grow slowly over time. They do not instantly consume everything around them. Instead, They attract material that is already nearby or falling in naturally. Black holes are extreme objects, but they follow the same laws of motion and gravity as everything else in the universe. Their power is immense, but it works in a precise, predictable way, rather than an uncontrollable, all-consuming pull. Black holes are often imagined as terrifying objects that pull everything around them, but their gravity behaves just like any other object of the same mass when viewed from far away. If you are far enough from a black hole, its gravity is no stronger or stranger than that of a star or planet with the same mass. The unusual effects only happen when you get very close. For example, imagine a black hole with the same mass as the Sun. From Earth, 150 million kilometers away, we would feel no difference in gravity if the Sun were replaced by this black hole. Earth would continue orbiting in the same way, and nothing would suck us in. The black hole's gravity at that distance follows the normal laws of motion and attraction, just like any other massive object. The extreme behavior of black holes, such as bending light, slowing time, or pulling matter in, only happens near the event horizon, the boundary beyond which nothing can escape. Outside this region, gravity weakens with distance in the usual way. Stars, planets, and even other black holes in the galaxy can orbit safely as long as they stay far enough away. This principle is important for understanding the universe. Even though black holes are incredibly dense and strange, they do not create a special suction that reaches across space. Their mass determines how they influence other objects, and the effects decrease with distance, just like the gravity of any planet or star. Recognizing this helps explain why black holes can exist in galaxies without immediately destroying everything around them. They may sit quietly at the center, influencing stars and gas over long distances, but only produce extreme effects close to themselves. Far away, their gravity is predictable and ordinary, no different from any object with the same mass. In short, black holes are not universal monsters. They are extreme in small regions near their centers, but from a distance, they behave like any other massive object. Their power is enormous, but it only becomes noticeable when you are very close. Beyond that, the universe continues as usual, and black holes obey the same gravitational rules as everything else. Black holes are usually thought of as objects hidden inside galaxies, but some scientists believe the reverse could be true. Galaxies may have grown around black holes, not the other way around. This idea is surprising because it challenges the way we imagine the formation of galaxies and their central supermassive black holes. The centers of most galaxies, including the Milky Way, contain supermassive black holes with millions or even billions of times the mass of the Sun. These black holes are tiny compared to the size of the galaxy, but they carry enormous gravitational influence. Some researchers suggest that in the early universe, black holes formed first, and their gravity attracted gas, dust, and other matter. Over time, this material collected and formed the stars, planets, and structures that make up galaxies. Evidence for this idea comes from observations of very young galaxies. Some galaxies appear to already contain massive black holes even before their full star systems have formed. This suggests that the black holes may have existed first, acting as seeds around which matter gathered. Their gravity would pull in gas and dust, allowing stars to form more quickly and helping the galaxy grow in an organized way. If true, this reverses the usual story of galaxy formation. Instead of a galaxy forming first and then a black hole appearing at its center, the black hole may guide the growth of the galaxy. This also helps explain why the mass of supermassive black holes is often closely related to the mass of the surrounding galaxy. Their presence is not an accident. They may be central to the galaxy's very structure and evolution. This possibility makes black holes even more mysterious. They are not just endpoints for matter or cosmic vacuum cleaners. They could be architects of galaxies, shaping the universe on the largest scales. Their influence is subtle but profound, silently guiding the assembly of billions of stars over billions of years. Black holes may not just exist in galaxies. They may have helped galaxies come into being at all. Supermassive black holes sit at the centers of galaxies, and their immense mass and gravity might make you think that removing one would destroy the entire galaxy instantly. Surprisingly, this is not the case. A galaxy is held together by the combined gravity of billions of stars, gas, and dark matter, not just the black hole at its center. While a supermassive black hole plays an important role, its removal would not immediately tear the galaxy apart. The stars in a galaxy orbit the center because of the total gravitational pull from all the matter, not just the black hole. Even without the central black hole, the stars would continue to follow their paths, though the very central regions might become less stable over long periods. The galaxy's structure is largely maintained by the distribution of mass in stars and dark matter throughout the galaxy, which far exceeds the mass of the black hole itself. A black hole does influence the surrounding stars and gas, especially in the inner region near the center. It can affect star formation, heat gas in the core, and even trigger certain movements of matter. But its absence would be felt gradually rather than instantly. Over time, the core of the galaxy might become slightly less dense or more chaotic, but the galaxy as a whole would continue to exist. This insight comes from simulations and observations of galaxies. Scientists can model what would happen if a central black hole were suddenly removed. The results show that while the central dynamics change, the galaxy does not collapse. Its vast outer regions, including billions of stars and dark matter, continue their orbits unaffected. The black hole is important, but it is not the glue holding the galaxy together entirely. Understanding this shows that black holes, even supermassive ones, are powerful but not omnipotent. They shape galaxies and influence their centers, but the overall structure of a galaxy is determined by the combined gravity of all its matter. Removing a black hole would create long-term changes, but it would not instantly destroy the beautiful, vast system of stars orbiting quietly in the galaxy. Not all black holes consume matter steadily. Some feed in bursts, gorging on gas, dust, or even stars for a short period, and then they can remain completely inactive for millions of years. This behavior makes them unpredictable and fascinating, showing that black holes are not constantly hungry, but instead operate in cycles depending on the material available around them. When a black hole has access to nearby matter, it can create an accretion disk, a swirling ring of gas and dust spiraling inward. Friction and gravitational forces heat the material to extreme temperatures, causing it to glow brightly in X-rays and other high-energy radiation. During this active feeding phase, the black hole seems violent and energetic, consuming large amounts of matter in a relatively short time. These bursts can make the black hole appear extremely bright, even visible from millions of light-years away. However, once the nearby material is used up or pushed away by radiation and energy from the accretion disk, the black hole enters a long period of inactivity. During this phase, there is little or nothing falling in. The black hole remains invisible because it does not emit light or sound on its own. From Earth, it would appear as just empty space, silently waiting for its next meal. This cycle can repeat many times over millions of years. A black hole may go through multiple feeding events, each separated by long periods of dormancy. These bursts are influenced by the environment, such as nearby stars shedding gas, collisions between clouds of matter, or material falling from the galaxy's core. Scientists study these bursts by observing X-ray flares and other energetic emissions, which reveal the black hole's feeding patterns without needing to see it directly. The fact that black holes eat in bursts shows that they are not mindless monsters. Their activity is closely tied to the availability of matter and the physics of their surroundings. They can be both extremely destructive during a feeding event and nearly invisible for millions of years, demonstrating the quiet, patient, and cyclical nature of these mysterious objects at the heart of galaxies. Black holes are often thought of as destructive forces, swallowing everything in their path. But some black holes can also play a surprising role in creating new stars. This happens through the powerful jets of energy and particles they sometimes shoot out from their poles. These jets are narrow, high-speed streams of matter, moving at close to the speed of light, and they can reach far into the surrounding galaxy. When these jets collide with clouds of gas and dust in space, they can compress the material. This compression increases pressure and density inside the clouds, creating the right conditions for gravity to pull the gas together into clumps. These clumps can collapse further and eventually form new stars. In this way, a black hole, which seems like a force of destruction, can indirectly trigger the birth of new stars far from its center. Not all black holes produce jets, but those that do can have a huge impact on their galaxy. The energy from the jets travels thousands or even millions of light years, shaping the interstellar medium and influencing star formation over a wide area. Sometimes, the jets even clear out pockets of gas, but in other areas, they compress the clouds enough to start a chain reaction of star formation. Astronomers have observed galaxies where jets from the central black hole seem to coincide with regions of intense star formation. By studying the light from these galaxies, they can see where gas is being compressed and new stars are forming, providing evidence that black holes are not only consumers of matter, but also creators of life in a cosmic sense. This phenomenon shows that black holes are not just simple destructive objects. They are dynamic and complex, capable of influencing their environment in ways that promote creation as well as destruction. Their jets, while extremely powerful, help shape galaxies and can kickstart the formation of stars, demonstrating that black holes play a critical and surprising role in the life cycle of the universe. Black holes might seem like chaotic objects, spinning randomly in space, but over millions of years, they can actually align themselves with their galaxies. This surprising behavior is connected to the way black holes interact with the surrounding matter, including gas, dust, and stars. Over time, these interactions can influence the black hole's spin and orientation, gradually bringing it into alignment with the larger structure of the galaxy. The process begins when a black hole accretes, or pulls in, gas and dust from the galaxy. Most galaxies rotate in a particular direction, so the material falling toward the black hole tends to carry angular momentum aligned with the galaxy's rotation. As the black hole absorbs this material, it gradually adjusts its spin to match the flow. The more matter it consumes over time, the stronger this alignment becomes, and the black hole's rotation can eventually point in the same direction as the galaxy's overall spin. This alignment has observable effects. When a black hole produces jets of high-energy particles, the jets often point along the black hole's spin axis. If the black hole is aligned with the galaxy, the jets are more likely to emerge perpendicular to the plane of the galaxy. This orientation can influence the movement of gas in the galaxy, affecting star formation and the overall dynamics of the galaxy's core. Interestingly, this alignment process is not quick. It can take millions to billions of years, depending on the size of the black hole and the amount of material it consumes. Smaller black holes in smaller galaxies may align faster, while supermassive black holes in large galaxies take much longer. Even collisions with other galaxies or black holes can temporarily disrupt alignment, but the process tends to resume over cosmic timescales. The fact that black holes can align with their galaxies shows how connected they are to the systems around them. They are not isolated objects floating randomly in space. Instead, black holes respond to their environment, gradually becoming part of the larger cosmic order. Over time, their spin and orientation reflect the history and motion of the galaxies they inhabit, highlighting the quiet but powerful influence they exert across the universe. A spinning black hole does more than just rotate itself. It actually twists the space around it. This effect, called frame dragging, means that the black hole's spin pulls nearby space along with it, almost as if space itself is being carried in a whirlpool. This is one of the strangest and most fascinating behaviors of spinning black holes, showing how extreme gravity can bend not just matter, but the fabric of space and time itself. Frame dragging happens because of the intense gravity near a black hole. When a black hole spins, it drags the surrounding spacetime along. Objects near the black hole are affected even if they are not in direct contact with it. A particle, a star, or a cloud of gas that moves close to a spinning black hole will feel this twisting effect, and its path will bend in the direction of the black hole's rotation. The faster the spin, the stronger the effect, making the motion of nearby matter noticeably influenced by the black hole's rotation. This phenomenon also has implications for the black hole's accretion disk. The gas and dust spiraling into the black hole tend to align with the spin because space itself is being dragged. As a result, the inner part of the disk can rotate in sync with the black hole, and jets of energy shooting from the poles of the black hole are also influenced by this frame dragging. It changes the dynamics of matter in extreme ways, creating patterns and movements that are completely different from normal space. Frame dragging is not just theoretical. Scientists have observed similar effects around Earth, although on an extremely small scale, confirming the predictions of Einstein's theory of general relativity. Around a spinning black hole, the effect is enormous. Space itself twists, and nothing can resist this motion near the event horizon. This shows that black holes are more than simple objects with mass and gravity. Their rotation can shape the very structure of space around them. A spinning black hole can twist, pull, and carry the universe near it in ways that are impossible in normal conditions, making them some of the most extreme and mind-bending objects in the cosmos. A spinning black hole does more than just twist space. It can control how matter moves near it. Because of the frame dragging effect, matter close to the black hole is forced to orbit in the same direction as the black hole's spin. Any attempt to move in the opposite direction becomes unstable or impossible, meaning that the spin of the black hole sets a cosmic rule for how nearby objects can circle it. This happens because the black hole is not just rotating itself, but dragging spacetime along with it. In the region near the event horizon, space is literally being pulled in the direction of the spin. Particles, gas, and dust trying to move against this pull are effectively fighting the motion of space itself. The result is that only co-rotating orbits, those aligned with the black hole's spin, can exist close to the horizon. Counter-rotating matter either cannot maintain a stable orbit or is pushed outward to safer distances. The effect is most noticeable in the accretion disk, the ring of hot gas and dust spiraling into the black hole. The inner parts of the disk are dominated by the black hole's rotation. Gas particles in these regions are forced to orbit in the same direction, creating a smooth, organized flow. This also influences how matter falls into the black hole and how energy is released, which can affect the brightness of the disk and the jets shooting out from the poles. This phenomenon shows how extreme black holes are. Unlike stars or planets, which allow matter to orbit in any direction, a spinning black hole can dictate motion near it. Its influence is not just through gravity, but also through the twisting of space itself, forcing matter to follow a single, unified path. The idea that a black hole can control the direction of motion highlights its dominance over the nearby universe. Matter cannot resist its pull and the twisting of space. In this way, spinning black holes do not just attract matter, they orchestrate its motion, shaping the flow of gas and dust around them, and imposing order in one of the most extreme environments in the cosmos. When two black holes meet, they do something that seems almost impossible. They merge more cleanly than any other objects in the universe. Unlike stars or planets, which can collide with massive explosions, shockwaves, and scattering debris, black holes join together in a surprisingly smooth process. This is because they are defined entirely by their mass, spin, and charge, with no solid surface or material to break apart. As the black holes orbit each other, they spiral closer and closer due to the emission of gravitational waves, ripples in spacetime predicted by Einstein and first directly detected in 2015. These waves carry energy away from the system, allowing the two black holes to gradually lose orbital distance until they finally collide. The collision itself is incredibly efficient. The two black holes merge into a single, larger black hole with a mass slightly less than the sum of the originals. Because a small portion of mass is converted directly into energy, released as gravitational waves. Unlike ordinary collisions, there is no messy explosion of matter. No material is ejected, and there is no chaotic scattering of debris. Black holes are pure gravitational objects, so when they merge, the result is simple. One larger black hole with a new spin and a smooth, spherical shape. The process is so clean that scientists can predict it accurately using equations from general relativity. The gravitational waves produced during a merger ripple across the universe, carrying information about the masses and spins of the black holes. By detecting these waves, astronomers can hear the collision and study black holes that would otherwise remain invisible. In fact, black hole mergers have become one of the most important ways to learn about these mysterious objects. This clean merging process is unique in the universe. Stars, planets, and galaxies all collide in violent, messy ways, producing chaos, explosions, and scattering of matter. Black holes, however, merge almost perfectly, showing the strange elegance of these cosmic objects. They are extreme, powerful, and mysterious, yet capable of combining with astonishing precision, leaving behind nothing but a new, larger black hole and ripples through spacetime itself. When two black holes merge, the energy released is unlike anything else in the universe. For a brief moment, the power of the collision can outshine all the stars in every galaxy combined. This incredible energy is not light, heat, or radiation in the usual sense. It is carried by gravitational waves, ripples in spacetime that move outward at the speed of light. These waves stretch and squeeze space itself, traveling across the universe and giving astronomers a way to detect black hole mergers billions of light years away. The reason the energy is so enormous comes from the mass of the black holes. When they collide, a small fraction of their total mass is converted directly into energy, following Einstein's famous equation, E equals mc2. Even though it may be just a few percent of their mass, the result is staggering. In just a fraction of a second, the energy released in gravitational waves can equal more than all the light produced by every star in the observable universe combined. It is a brief but mind-boggling demonstration of the extreme power of black holes. Despite the incredible energy, the merger is silent in the normal sense. No light or sound reaches us directly from the collision unless there is surrounding matter to produce electromagnetic radiation. Instead, the energy moves through space as distortions of spacetime itself, which can be measured with sensitive detectors like LIGO and Virgo. These instruments can detect tiny changes in distance caused by passing gravitational waves, allowing scientists to hear the black hole collision across vast distances. This momentary burst of energy shows the raw, extreme forces at work in the universe. Black holes, often invisible and quiet most of the time, can become the most powerful events imaginable when they merge. The merger illustrates the strange contrast of black holes. Objects that seem invisible and calm can release more energy in a second than billions of stars do over their entire lifetimes. In short, black hole mergers are cosmic fireworks on a scale far beyond anything we normally experience. The energy they release in gravitational waves briefly makes them the most powerful events in the universe, proving that even objects hidden in darkness can dominate the cosmos in spectacular, unforgettable ways. Black holes are mysterious in ways we still do not fully understand, especially when it comes to information. For a long time, scientists believed that anything falling into a black hole, matter, energy, even the details of its structure, was lost forever. But modern theories suggest that black holes may preserve information in ways we cannot yet observe, hiding it in the universe instead of destroying it. This idea comes from the strange connection between black holes, quantum mechanics, and the laws of physics. Even though a black hole's gravity is so strong that nothing can escape its event horizon, the information about what fell in might still exist on the surface of the black hole, encoded in some way we do not yet fully understand. This is sometimes referred to as the holographic principle, where the surface of the black hole acts like a two-dimensional record of all the three-dimensional objects it has swallowed. If true, this could solve a major puzzle in physics called the information paradox. According to quantum mechanics, information cannot be destroyed, but black holes seem to contradict this rule because anything inside them could not escape. By storing information on the event horizon or in subtle forms of radiation, black holes might preserve this information without letting it interact directly with the rest of the universe. The fascinating part is that this information could remain hidden for billions of years, completely invisible to us. We cannot see it or measure it directly, but it may exist as tiny patterns in the energy emitted from the black hole or as distortions in space-time. It is possible that one day scientists will develop new ways to detect these hidden traces and finally understand how black holes keep secrets of the universe. This idea shows that black holes are not just destructive. They may also be the universe's ultimate record keepers, quietly storing information about everything they encounter. Even in darkness, black holes could be preserving the history of matter, energy, and perhaps even the events of the universe itself, waiting for us to uncover their hidden stories. Black holes are not just strange objects. They may hold the key to one of the biggest mysteries in science, unifying all known physics. For over a century, scientists have struggled to connect the two major theories of the universe. On one hand, we have general relativity, which describes gravity and the motion of planets, stars, and galaxies. On the other hand, we have quantum mechanics, which explains how the tiniest particles behave. These two frameworks work perfectly in their own domains, but they seem incompatible when applied together. Black holes, however, exist at the intersection of both. At the center of a black hole, gravity becomes incredibly strong, and matter is compressed into extremely small regions. This is exactly where the rules of quantum mechanics should apply, but general relativity predicts a singularity, an infinitely dense point where the laws of physics break down. Scientists believe that understanding what happens inside black holes could reveal a deeper theory that unites gravity with quantum mechanics, a theory of everything. Hawking radiation is one example of this intersection. It shows that black holes are affected by quantum processes even though they are enormous and dominated by gravity. The way black holes interact with information, energy, and spacetime may provide clues about how these two seemingly incompatible frameworks can fit together. Studying the surface, spin, and evaporation of black holes could uncover principles that govern both large-scale cosmic events and tiny quantum phenomena simultaneously. Because black holes push the laws of physics to their limits, they act as natural laboratories for extreme conditions that cannot be reproduced on Earth. Observing them, modeling their behavior, and detecting the gravitational waves or radiation they emit may help physicists find patterns that link general relativity and quantum mechanics. In this sense, black holes are not just destructive objects. They may hold the answers to some of the universe's deepest questions. They represent a bridge between the very large and the very small, offering clues about how all the forces of nature could work together in a single, unified framework. Unlocking their secrets might finally allow scientists to understand the universe at every scale, from the tiniest particles to the largest cosmic structures. Black holes are some of the most extreme objects in the universe, with gravity so strong that nothing can escape once it passes the event horizon. They crush matter to incredible densities, twist space and time, and bend light in ways that seem impossible. Yet, despite all these extremes, black holes are also remarkably stable. Once formed, they can exist for billions of years with very little change, making them some of the most reliable structures in the cosmos. This stability comes from the simplicity of a black hole's properties. A black hole can be completely described by just a few characteristics: its mass, spin, and charge. Unlike stars or planets, it has no solid surface, no atmosphere, and no complex internal structure that could break apart. Because of this, black holes do not suffer from the same kinds of instabilities that other objects experience. They are essentially pure solutions to the equations of general relativity, which makes them incredibly steady over time. Even when black holes interact with matter, such as pulling in gas from a nearby star, they remain fundamentally unchanged. The event horizon may grow slightly as mass is added, but the black hole's overall structure and stability persist. Similarly, black holes can merge, producing gravitational waves, and yet the resulting single black hole quickly settles into a stable form again. These mergers demonstrate how black holes can withstand enormous forces and still remain consistent with their defining properties. Their stability also makes them important for understanding the universe. Supermassive black holes at the centers of galaxies have likely existed for most of the galaxy's lifetime, quietly influencing star formation, gas motion, and galactic evolution without collapsing or breaking apart. Even small black holes formed from collapsed stars can persist for longer than the current age of the universe if they are not actively evaporating. In a way, black holes are the ultimate cosmic anchors. While everything around them may change, collide, or explode, a black hole remains steady, governed by simple but extreme physical laws. Their ability to endure over unimaginable time and extreme conditions shows that these mysterious objects are not only powerful but also remarkably stable, standing as silent witnesses to the universe's history. Black holes are often thought of as eternal, unchanging objects that consume everything in their path. But theories about the far future of the universe suggest an even stranger possibility. The universe may end with black holes fading quietly into nothing. Over unimaginably long timescales, even the largest black holes are not permanent. They slowly lose mass through a process called Hawking radiation, eventually disappearing completely. This evaporation happens incredibly slowly for supermassive black holes. A black hole with millions or billions of times, the sun's mass would take far longer than the current age of the universe to vanish. During this time, it emits tiny amounts of energy, so faint that it is almost impossible to detect. The black hole remains silent and invisible, quietly shrinking over billions or trillions of years. Its event horizon gradually becomes smaller, and the energy it releases contributes to the background of the universe without creating light or sound in the way stars do. Eventually, when a black hole loses most of its mass, the final stage of evaporation accelerates. In a tiny fraction of a second compared to its long history, the black hole could vanish entirely, leaving behind no solid matter, no light, and no gravitational footprint. The disappearance is complete, returning the energy to the universe in the form of subtle radiation. Unlike explosions or collisions, this process is quiet and almost ghost-like, a peaceful end for one of the most extreme objects in existence. If this process continues for all black holes, the universe could slowly become a much emptier place. Stars would burn out, galaxies would disperse, and black holes, the final remnants of matter, would fade quietly into nothing. Over unimaginable timescales, all that would remain is a cold, dark, and nearly empty universe, where the memory of these extraordinary objects exists only in the energy they left behind. This idea is both eerie and fascinating. Black holes, which seem so powerful and eternal, are not permanent. Their quiet evaporation shows that even the most extreme objects have an ending, and it may be the universe itself that slowly fades, leaving behind a vast cosmic silence. In the grandest sense, the final act of the universe could be defined not by fire and destruction, but by black holes disappearing quietly, one by one, into nothing.